Imagine a company spends 6 months building new feature. Product team is excited. Engineers are confident. Leadership expects results. So they run an experiment. Thousands of users participate. Data is collected. Statistical tests are performed. And the conclusion is no effect. Feature failed. Project is cancelled. Case closed. Except months later, another team tests similar idea, and this time, huge improvement. So, what happened? Was the first experiment wrong? Not necessarily. Analysis may have been perfect, statistics may have been correct, but the experiment itself may have been poorly designed because good decisions don't start with data analysis, they start with experiment design. Before any data is collected, p values are calculated and dashboards are built, quality of result is already being determined. And that is why experiment design is one of the most important skills in statistics, data science, product analytics, and scientific research. Welcome back to Shital's Data Desk. I am Shital, and in this video, we will break down below topics one by one. By the end of this video, you will understand how great experiments are designed before single data point is collected. So, let's start with the foundation. What exactly is experiment design? Experiment design is the process of planning an experiment before it begins. It defines what will be tested, who will be tested, how results will be measured, how decisions will be made. A common misconception is that experimentation begins when data arrives. It doesn't. Experimentation begins with planning. Because once data is collected, many mistakes become impossible to fix. Bad randomization, wrong metrics, insufficient sample size, biased participant collection. These problems cannot be solved later with better statistics. Experiment design exists to prevent those mistakes before they happen. But before designing any experiment, we first need to know exactly what problem we are trying to solve. Every experiment starts with a question. And surprisingly, many experiments fail because question itself is vague. Imagine asking, is the new feature better? Better how? More revenue, more engagement, more retention, faster onboarding, lower churn? The question is unclear. Good experiments begin with specific hypotheses. For example, new onboarding flow will increase activation rate by 5%. Notice the difference. It is measurable, specific, testable. This stage is called hypothesis formulation. And a strong hypothesis gives entire experiment direction. Once we know what we are trying to improve, we need a way to measure it. Metrics are the language of experimentation. And choosing the wrong metrics can completely invalidate experiment. Most experiments use three types of metrics: primary metrics, guardrail metrics, and diagnostic metrics. Primary metrics determine success. For example, conversion rate. Guardrail metrics ensure nothing important gets worse. For example, customer complaints. Diagnostic metrics help explain why results occurred. For example, time spent on page. Good experiment design requires all three. Because success is not just about improving one number, it is about improving right number. Once the metrics are chosen, we need something to compare against. Experiments are fundamentally comparison systems. Treatment group receives change, control group does not. Without control group, we never know what would have happened anyway. Maybe revenue increased because of the feature, or maybe it increased because of holiday. Control group helps isolate causality. This is why A/B testing is so powerful. Both groups experience same world except for one difference, the treatment. But even control groups can fail if users are assigned incorrectly. Randomization is the engine that makes experimentation work. Its job is simple: make groups comparable. Without randomization, hidden differences can contaminate results. Maybe younger users receive new feature. Maybe high spending customers accidentally cluster in one group. Now we can no longer tell whether results came from treatment or from user differences. Randomization reduces this risk. It balances known and unknown factors and transforms correlation into something much closer to causation. Now that our groups are properly formed, we must decide how much data to collect. This is where many experiments fail before they even begin. Too little data, real effects may be missed. Too much data, experiments become expensive, slow, and inefficient. So, before launching an experiment, we need to decide four critical things: minimum detectable effect or MDE, alpha, statistical power, and variability. These inputs are then used in something called power analysis. Power analysis calculates sample size required for the experiment. In other words, it tells us how much data we need before we can trust the results. This helps ensure that experiment has a realistic chance of detecting meaningful improvements if they truly exist. But sometimes there's a problem. Required sample size may be enormous. Maybe your website doesn't have enough traffic. Maybe waiting 6 months for results is not realistic. So instead of collecting more users, companies often look for another solution: reducing noise. One popular technique for doing this is called Cupid. Instead of relying only on data collected during experiment, Cupid also uses information about user behavior before experiment started. This helps explain away some of natural differences between users. And when variability decreases, experiment becomes more efficient. Less variability means higher statistical power, smaller sample size requirements, faster experiments, and in some situations, Cupid can dramatically reduce how long an experiment needs to run. But even perfectly powered experiments can still produce misleading conclusions if experiment itself is flawed. This is where experiment design becomes especially important because not all errors come from randomness. Some come from the way experiment is conducted. These are called biases. Bias occurs when systematic errors distort results in consistent direction. Examples: selection bias, measurement bias, survivorship bias, sampling bias, and all of them can lead us towards incorrect conclusions. Then there are confounding variables. A confounder is a hidden factor that influences both treatment and outcome. And confounders can create relationships that appear real but actually are not. For example, ice cream sales increases during summer. Drowning also increases during summer. Does ice cream causes drowning? Of course not. Real driver is temperature. Temperature affects both variables. Temperature is confounder. And because of confounders, correlation alone can be dangerously misleading. One of the primary goals of experiment design is to eliminate or control these hidden influences. Because statistical significance means very little if experiment itself is fundamentally flawed. Another common challenge is something called novelty effect. Sometimes users react positively simply because something is new. Initial excitement creates temporary boost in performance. But once novelty wears off, improvement disappears. That is why many experiments must run long enough to measure sustained behavior rather than temporary excitement. So once experiment has been designed properly and launched successfully, challenge shifts from planning to execution. Launching an experiment does not mean work is finished. Now we need to make sure experiment is behaving correctly. One useful technique is called AA test. In an AA test, both groups receive exactly same experience. No new feature, no treatment, no differences at all. The purpose is not to test product. It is to test the experimentation system itself. Because if identical groups produce statistically significant differences, something is wrong. Maybe randomization process is broken. Maybe tracking system is failing. Maybe experimentation framework itself cannot be trusted. And once real experiment begins, we continuously monitor several things: data quality, traffic allocation, sample ratio mismatch or SRM, tracking failures, unexpected user behavior. One particularly important warning signal is SRM. Suppose you plan 50-50 traffic split, but somehow experiment starts assigning users in 60-40 ratio. That imbalance may indicate serious problem with randomization, tracking or experiment assignment. SRM acts like an alarm bell telling us something may be wrong. Another common mistake is peaking. Checking results every day and stopping experiment the moment significance appears. While this feels harmless, it dramatically increases false positives. Good experimenters commit to predefined plan because changing rules midway through the experiment can invalidate results. Eventually, experiment reaches its planned endpoint, and that is when we face question everyone cares about. When results arrive, many people immediately ask, is it statistically significant? But that is only part of the story. We also need to ask, how large is the effect? Is it practically meaningful? Is it worth implementing? A tiny statistical significant improvement may have almost no business value. Meanwhile, a large effect with some uncertainty may still be worth further investigation. Good experiment design doesn't optimize for significance. It optimizes for decisions. Because goal is not proving hypothesis. The goal is making better choices. We should also examine confidence intervals. Confidence intervals show the range of effect sizes that are reasonably consistent with data. Two experiments may report same average effect but have very different level of uncertainty. Looking only at single point estimate can be misleading. And then there is one of the most fascinating traps in all of statistics. Simpson's paradox. This occurs when result appears positive in the overall data but reverses when data is broken into meaningful subgroups. A feature might look like winner overall, but when analyzed separately by country, device type, or customer segment, it may actually lose everywhere. That is why great analysts never rely solely on high level averages. They also investigate what is happening beneath the surface. But even if experiment is perfectly randomized, properly monitored, and correctly analyzed, one final question remains. Can these results actually be trusted outside this specific experiment? To answer that question, statisticians distinguish between two different types of validity: internal validity and external validity. Internal validity asks, can we trust the causal conclusion inside this experiment? If experiment was randomized correctly, confounders were controlled, and treatment was isolated properly, then internal validity is high. We can confidently say treatment caused the observed outcome. But external validity asks completely different question. Will these results generalize to the real world? And this is where many organizations run into trouble. Imagine you run an experiment only on premium desktop users in United States during major holiday shopping weekend. Your experiment might be internally flawless. Causal conclusion may be completely correct. But will those results also apply to mobile users, international customers, different seasons, different market conditions? Maybe or maybe not. That is the challenge of external validity. It is about determining whether conclusions extend beyond specific environment in which they were discovered. And truly, great experiment design considers both. Not only whether result is correct, but whether result is useful beyond experiment itself. Because local truth is not always universal truth. And here's the deeper truth. Most people think experiments produce knowledge. They don't. Experiments reduce uncertainty. And the quality of that uncertainty reduction depends almost entirely on the design. Bad analysis can sometimes be corrected. Bad experiment design usually cannot. Because once data is collected, opportunity to design experiment is gone. That is why great analysts spend so much time planning. Not because planning is exciting, but because every trustworthy conclusion begins long before first observation is recorded. And that's what experiment design really is. The art of creating conditions where truth has the best chance of revealing itself. If you found this video helpful, don't forget to like, share, and subscribe to Shital's Data Desk. Thanks for watching, and I'll see you in the next video.